Hello, I'm just going to finish off those 3 examples for solids of revolution that we didn't have time to cover today. So let's go. Okay, so here we're trying to find the volume of the solid obtained by rotating the region bounded by xy is equal to 1, y is equal to 0, x is equal to 1, and x is equal to 2, about x is equal to -1. So let's start by sketching what we've got. The axis of rotation is x equal to -1. So let's put that there. Maybe I'll use a dotted line just for fun. And then we've got xy is equal to 1. So I've already shown here that we can rewrite that to just be the same as the function y is equal to 1 over x. So we know what that looks like. And you know what? Because we're rotating about a vertical line, let's integrate over y. And so we'll use this function in the form x is equal to 1 over y. Okay, and then we're also bounded by y is equal to 0, so that means we're above the x-axis. And then the lines x is equal to 1 and x is equal to 2. So let's say we've got this and this, and that will define our area. I'll color it in. Okay, so if we look here, we've got 2 areas kind of that we have to think about, because as we rotate this whole region about the x is equal to 1 line, we see that we get a shape that's kind of got 2 parts to it. We've got this curved part, and then we've got the straight up and down part. So this is the shape we're dealing with. Kind of, and then it's like hollow on the inside, like that. And so because of that, and the changes to what the outer radius is, we'll have to consider things slightly differently. So what I'm going to do is break up this region into region 1 and region 2. For region 1, our inner radius is just, so we're going to the line x is equal to 1, but we've also got this -1. So the inner radius is just always 2 units. And you know what? It's the same for R2, so we can just do that as well. Okay, and then our outer radius, that's again where things change. So for the first region, we can see that the outer radius between the axis of revolution and the outside of the region corresponds to that graph 1 over y. Whereas, I guess I'll not draw that right there, maybe just above. This outer radius is, well, it's 2 units from the positive x-axis, and then that, it's 3 units. 1 plus 3, because this is 1 and this is 2. So we've got now 2 different regions where we're making a solid of revolution for each of them and putting them one on top of each other. That's okay. That's totally a fine way to calculate a volume. All right, and then the only other thing that we need are the bounds of integration for each of these regions. Well, let's find the coordinates of these points. Here, x is equal to 1 intersects the line x is equal to 1 intersects our function x is equal to 1 over y at 1, 1. And then the line x is equal to 2 intersects that function at 2, 1/2. And so we can see that the values of y that we range over for R1 are from 1/2 to 1. And then the range of y values that we use for R2 is going to be from 0 to 1/2. So again, if we want to kind of like split it up into two here, this is the solid of revolution that we get from R1, and this one is R2. And so then the total volume is going to be, so for, okay, I'm just trying to find the nice way to label everything. Let's do the one for R1 here. And then the one for R2 will go there. So we've got, for R1, we're going from the y values of 1/2 to 1. And then we've got, again, outer radius. Oh, shoot, I just realized, sorry, the outer radius here, if you caught that, it's not 1 over y, it's 1 over y plus 1, because we're going that extra 1 unit. So that points to anyone who was like, wait a second. Okay, so our outer radius is that 1 over y plus 1 squared. And then our inner radius, we know is 2, so we go minus 2 squared dy. And then same thing for the one for region 2. We go from 0 to 1/2 of, well, 3 squared minus 2 squared dy. That volume that we get from region 2, you might notice it's just a rectangle rotated around. So it really is just like a washer shape, just one big one. So that's not a hard volume to calculate. It's just the other one on top that's kind of weird. Cool. So I'm not going to work that one out. I kind of just wanted to set it up for us. So that's that example. The next one I think is kind of cool because there are infinitely many solutions really for this one. You can get creative with it. So I hope you've had a chance to look at it. So here, this is kind of backwards. We're given an integral, and we're asked to find a solid that it could represent. So comparing this formula to what we've seen before, we want to see if we can find what the function and the region could be. So if we compare it to the washer method formula, that says that volume is equal to pi, some bounds of integration a and b, and then it's the outer radius squared minus this is the inner radius squared times dx. And so here it looks like we can try outer radius is 1 plus cos x. And our inner radius, let's say, is just 1. And then a is 0, b is pi over 2. And so we can sketch it out. I always love to sketch it out. So 1 plus cos x, that's just the function 1, or that's just the function cos x, essentially like shifted up by 1. So instead of going, like this, we're moving it up by 1. Oh, you know what? I guess I can just literally do that. Isn't that cool? Actually, no, I won't do that because I want to kind of stretch it out. So it starts at 2, let's say, and then kind of goes down to 1 when the angle is pi over 2. So here, this is y is equal to 1 plus cos x. And then we've also got here the line y is equal to 1. Then that's our inner radius if we're revolving around the x-axis. And then the outer radius is that 1 plus cos x. So I'll just write a sentence kind of tying it together. You can say, this is the volume of the solid formed by rotating the region bounded by y is equal to 1 plus cos x, y is equal to 1, and x is equal to 0. Yeah, I guess we need that too, just to clarify that we don't want to extend further into that quadrant. About the x-axis. Now I said that there are infinitely many solutions because you can choose to maybe rotate about a different axis. So you could also say that we're maybe just taking the graph of y is equal to cos x and rotating that about the axis y is equal to -1. So we could also say this is the region bounded by y is equal to cos x, y is equal to 0, x is equal to 0. Rotated about the line y is equal to -1. And we could keep just choosing different axes as long as we get that particular step thing on the inside. It'll always be the same shape, just kind of shift it around space. Like it'll always be, let's see, so if I kind of sketch out what the shape is. So the region, we've got like this, and then this is our axis. So we kind of have, what if I go like that? Does that help? Okay, I'm gonna try that again. See, that's, I guess, a fun thing about watching the videos. You get the benefit of, okay, let's see. Maybe I'll do it this way from this angle. So we kind of have, you know what this is? This is like an olive. It's kind of like a olive, but we've like carved out the inside bit to put a pimento in there. And so then we could take this and just kind of put this anywhere around any axis. Just rotate it. So that's the region. That's how it ties together. Awesome. Okay, I think I just have the one more. And this one I think we get to use some geometry if we want. Okay, so here we're going to compute the volume of the solid formed by rotating the region bounded by the curves y is equal to 2y, x is equal to 0, and y is equal to 9 about the y-axis. All right, let's do a sketch, as always. Now, seeing it as x is equal to 2y, that's the same thing as y is equal to x over 2, if that helps for sketching. Because we can visualize what that looks like, right? That's like, whatever. We don't know what the, the scale is for these axes. This can be our line. X is equal to 2y. And then we're bounded by x is equal to 0, so the y-axis, and y is equal to 9. So that means the region that we're dealing with is this one. And because we're rotating this about the y-axis to produce a solid, you can see that this is a disk method one because there's no gap between the axis and the region. And like the solid that we would get would just be a perfect cone like that. All right, so we just need to find the one radius. And that's not too bad at all. That's just going from the y-axis to this x-coordinate, which is given by 2y, as we let y vary from 0 to 9. And so our volume is pi 0 to 9 2y squared dy. And if we actually compute this, we can take the 4 pi out, then we get the integral from 0 to 9 of y squared dy. So that's 4 pi y cubed over 3, evaluated at 0 and 9, which just gives us 4 pi 9 cubed over 3. Now you'll notice that this is just a cone with height 9 and base radius 18. Because if we look at what the point here is, this is the point 18, 9. So we can just use the volume formula for a cone. And so you can say this is V is equal to pi r squared h over 3. So that's pi 18 squared times 9 over 3, which also gives us 4 pi 9 cubed over 3 as well. So that's a cool fact. The volume of a cone is always a third of what the volume would be for the sphere. So, you know, yeah. Or not the sphere, the cylinder. Cylinder are the same dimensions. So this is our H, and this is our R. That's just a third of the corresponding cylinder's volume. Awesome, I guess that's it. I'll do, yeah, because we'll do more cylindrical shells tomorrow. Did I leave any of those for exercise? Oh, I guess here I did, but you know, that's just some computation, so I'll do that now. Awesome. Well, if you watch this, thank you. Good job. I hope you tried these questions yourself as well. And again, at the end of this chapter, I've got a bunch of the textbook questions for both methods, so washer discs and cylindrical shells, as well as some of the answers. And if you want, and solutions, not just the answers. Isn't that a sleigh? But if you want help with the even numbered ones, then you can just check with me, because I am always happy to talk about math. All right, bye.